website, connect with them on LinkedIn, etc. But for now, I'm pleased to introduce our next speaker, Mike D., Associate Forensic Chemist with Montrose Environmental Group. His session explores how statistical tools can simplify large, complex chemical data sets into clear visualizations that support defensible expert testimony, especially in legal contexts where clarity and transparency are critical. He'll demonstrate how multiple chemical measurements can be distilled into intuitive figures that highlight meaningful patterns while acknowledging uncertainty and avoiding overinterpretation. Please welcome to the stage Mike D. with his session, Crunching Numbers, Not Nerves, Making Stats Courtroom Friendly.
Okay, I wanted to start off by saying sorry to everyone who's missing the hockey game. If Canada scores at any time during this, feel free to yell. Let me just get the pointer out. So, before we jump into my niche presentation about environmental forensics, I want to start with a slightly different topic, how we memorize information. Complex, quantitative information is hard to memorize. So often, if you can associate it with an image, or even better, a story, it's easier to retain that information. So everyone, take a look at the screen. What's the first thing that comes to mind? I do this for every single presentation I do. The crazier the better, that's how the memory works. And by the end of the presentation, hopefully my whole entire story is encompassed in this one image here. But before I talk about what these images mean, I have to give a little introduction on who I am. For those who I haven't met, my name is Mike Dereviankin. I'm the Associate Forensic Chemist at Montrose Environmental. When people hear forensic chemistry, they think of CSI. I always have to clarify, that's not what I do. I am just a consultant that answers one really deceptively easy question. How does one sample compare to another sample? And this seems like a deceptively easy question, but it's a very expensive one. So pose yourself in this situation. Let's say you're working on a $2 billion cleanup site, and you're the expert witness who's retained on the site. If I say my client is 46% responsible, and the opposition says my client is 48% responsible, we're gonna argue for years on end because 2% of $2 billion is a lot of money. So, most of my work revolves around litigation, expert witness testimony, and chemical data scientists like myself. We can work on two different kind of projects. Project one, you could work for the defense. This is usually the big bad chemical manufacturer being accused of malpractice. Or you could work for the plaintiff. Usually that's a smaller scale law firm attacking the defense, and the claim of malpractice is made first, and the data follows that. So what dictates if there's a case? People think it's a simple story. If a concentration is high, above a regulatory limit, then there's a case. But it's actually not that. The real question is, how does this sample look like? What does the neighboring sample look like? What does the source look like? How accurately are we resembling the source? So now layer all this on top of, I have to explain this to a jury, a judge, and to the general public who don't really see this data on a daily basis and aren't really subject matter experts in this expertise. So how do we communicate this complex chemical data in a way that's intuitive, defensible, and easy to understand? And before I jump into the solution to all this, I have to do an analogy. Who remembers going to 7-Eleven as a kid? When I'd go to 7-Eleven as a kid, I would never get one flavor of Slurpee. I would mix them all together, and we'd call this swamp water. This swamp water is a perfect analogy of an environmental sample. It's a bunch of different sources mixed together. In my industry, we call these sources end members. And so my job is to figure out what are the sources in that mixture. And so how do you do this? Well, just like cooking, we're trying to understand recipes based on ingredients. So we can take that swamp water, put it into an analytical instrument, get all the different chemicals from there, and as chemists, we have a great understanding of what the recipes are. And so we can mathematically unmix what were the initial sources in that sample. So that sounds great, and why don't you do that all the time? I do, but here's the challenge. I'm not dealing with just one swamp water. I'm dealing with hundreds or thousands of different environmental samples. So how do I kind of explain this in a way that's intuitive, and then also layer this on top of litigation? If I'm doing this in front of a jury, I'm given 1 or 2 slides, and I'm given 10 minutes to do all this. So how do we solve this? There's a solution. It is called dimensionality reduction. And not to be the analogy guy, but I have to do one more analogy to kind of explain how we read these plots. So imagine you're hosting a scientific party and you want to understand all the interactions between all the different individuals at your party. Sure, you could talk to some individuals, but you won't really get the overall sense of the vibe and who's there and who's having what conversation. So what's your solution? Well, you could go onto the balcony of your party and then get a bird's eye view of what's going on. You can see all the different interactions. So generally what happens at parties is people who have shared interests will be beside each other talking about the same things. Let's say there's people talking about hockey on one side, people talking about skiing on the other side, and then people talking about the Stampede, keep it Calgary themed, on the other side. So people will be standing beside each other who have similar interests. People far away from each other will probably be different. And the same goes for our swamp waters. Similar swamp waters in these plots will be beside each other, and things that are chemically distinct will be far away from each other. The one thing to note about this plot right here is that if you're looking at it, you can see that the pure flavors are at the very ends. These pure flavors could represent distinct chemical manufacturers or chemical processes. So if an unknown sample is plotting near, let's say, the blue, we can say, well, this sample is more blue than anything else. If it's plotting in the middle, you can say, hey, this is a mixture. And this is just how we're starting to communicate all this complex chemical data into one simple visual. So let's do a real-world example. Hamilton Harbor is located west of Toronto. It's a historically known site for using coal tar manufacturing, steel manufacturing, and one of the chemicals of concern there is polyaromatic hydrocarbons, PHs for short. PHs are a class of chemical. It's not just one chemical, so you have thousands of different pH species that you could hypothetically measure. So the government of Ontario was really interested in knowing how are the chemicals traveling from the Hamilton Harbor into the other sediments. And the general consensus with most scientific explanations is that there's a source-receptor model. Source-receptor means that source, high concentration. Receptor, lower concentration, getting feed from the high concentration. That's a very simplistic way of looking at things. Sure, concentrations could connect, but what about the distinct chemical fingerprint? What about the swamp waters? Are they identical? And that's one of the questions we want to answer with dimensionality reduction. So here's my dimensionality reduction plot from the beginning of the slide, but now I'm layering information on top of it. The color is representative of where it's located in the site. Pink samples are from Hamilton Harbor, green samples are from outside Hamilton Harbor, and these blue samples are references. So these are actual product samples that we've taken to the lab and measured. When I saw this plot, the initial question was, why are Hamilton Harbor samples plotting so far away from the other samples? Well, then I kind of jumped into the data a bit more and I looked at, okay, when were these samples measured? So we collected these samples in 2014, we measured in 2014, and then that exact same sample got retaken to the lab and measured again in 2022. But what we're seeing is that the 2022 samples are very spread and far away from the 2014 samples. They have a distinctly different chemical fingerprint. But this is the exact same sample from the exact same vial measured at two different time points. It should have not changed at all. And so, hundreds of thousands of dollars of lab results later, and kind of my conclusion is this lab data is not good. And then they needed some validity to, why isn't it good, Mike? Tell me why isn't it good? Well, then I did some metadata. I said, who was the analyst who was measuring in 2014? Is it the same exact person? Do we have some human error here? Unfortunately, there was a different analyst in 2022, and every time they measured it, it seemed to be analytically different. Again, they brought me in to say, is Hamilton Harbor connected to Toronto? But the question actually changed. And the question now is this data good enough to actually be presented to the public? And unfortunately, there is a big subset of samples that did not align chemically. And then as a subject matter expert, I kind of looked into the chemical fingerprint and said, well, this is wishy-washy because of this and because of this analytical parameter. I did this presentation yesterday to my fiance, and she told me, hey, Mike, great presentation. What's the conclusion of all this? And I had to tell her, I don't know. Okay, so I came up with one this morning. My conclusion is that it's great to have one visual where you can defensively explain everything that's happening on a site. You might initially come in with one hypothesis, and that might change. Science is about having a hypothesis and testing it. Sometimes that hypothesis isn't right, and there needs to be an intuitive way to explain it to someone like a regulator. And so that's kind of the power of dimensionality reduction and UMAP and MikeMap. So if anyone is interested in what this does, how it's done, I make all my code publicly available, and I'm also happy to do some consulting work on the code. So feel free to ask any questions. Thank you.